Okay, so here's another group theory problem. I have a pretty long list of problems that I'm going to work on, so I guess they're all going to be group theory for now. Anyway, the problem says show that if, so these are all groups here, so that if G1 is isomorphic to H1 and G2 is isomorphic to H2, then the direct product of G1 and G2 is isomorphic to the direct product of H1 and H2. So I had just actually recorded a solution for this, and I made a mistake. I'll talk about it right now. So let's start with our assumption. So suppose that, of course, G1 is isomorphic to H1, and that G2 is isomorphic to H2. Since these are isomorphic to each other, then there exists an isomorphism between G1 and H1, and then an isomorphism between G2 and H2. So there exists isomorphisms, and we'll just pick a letter for the map. This is where I made a mistake when I first recorded this. I decided to use phi for one of the maps and then psi for the other one, but then they look very similar, and it was a problem because I couldn't keep track of what I was writing. So for the first one, we'll use phi, and then we'll use eta or something. I don't know. So there exists isomorphisms. We'll say phi from G1 to H1, and we'll use eta, I suppose. So eta from G2 to H2. Now we want to show that the direct product of G1 and G2 is isomorphic to the direct product of H1 and H2. So in order to show that they're isomorphism, we need to define a mapping, and then show that it's a homomorphism, and then show that it's a bijective homomorphism. Then we can claim that these, or not claim, but then we've proven that these two direct products are isomorphic to each other. So let's define a map. So we're going to define, I'm going to use pi, a map from G1 cross G2 to H1 cross H2. Now what this map is going to do is it's going to take elements in the direct product G1, G2. So we're going to say it takes ordered pairs, say G1, G2. These are elements in that direct product, and it's going to send them to the ordered pair phi of G1 and then eta of G2. Now we want to show that first we want to show that pi, what did I just write here? Show that pi is what am I writing? No, to show that pi is a homomorphism. Let's first just define some elements just to kind of organize our work here. So let's take G1 and G1 prime to be elements in G1, and G2 and G2 prime to be elements in G2. Let's recall, to show that this is a homomorphism, we want to show that if we take two elements in G1 cross G2 and operate them and then apply the map pi, that it's the same as applying the map pi to both of those elements and then operating them after. So we want to show that pi of G1, G2 operated with pi of G1 prime, G2 prime. We want to show that this is the same as pi of G1, G1 prime, G2, G2 prime. Showing this here will show that our map that we have defined is actually a homomorphism. Okay, so let's go ahead and proceed. So then pi of G1, G2, pi of G1 prime, G2 prime. Just by the way we've defined our map here, this is going to be equal to the ordered pair phi of G1, eta of G2, and then phi of G1 prime, comma, eta of G2 prime. Just from the way we've defined our map. Now, these two elements both live in H1 cross H2. Just from the construction of our map and what both phi and eta are doing. So they live in the same, they live in the codomain together. They're ordered pairs and we're operating them. So this is just component-wise operation. So this is just equal to phi of G1, phi of G2, eta of G1 prime, eta of G2 prime. Now here's where we want to use the fact that both phi and eta are isomorphisms. So let's go ahead and recall that. So recall phi and eta are isomorphisms. That's important because here, no, I wanted my highlighter. So here, this is just phi of G1, phi of G2. But if phi is an isomorphism, then this is just equal to phi of G1, G2. Similarly, this here on the right is just going to be eta of G1 prime, G2 prime. And this is exactly pi of G1, G1 prime, comma, G2, G2 prime. And we're going to make a quick edit because I messed up my notation here. So let me fix this. Okay. What's supposed to be in here? Phi of G1. This should be G1 prime here. Yeah, because we're matching up the phis, and then this should be G2 here. And then this should be G1 prime. And then this is G2. There you go. That fixes it. Okay, so let's see, what have we shown here? Okay, thus pi is a homomorphism. So, thus pi is a homomorphism. Okay, that's about half the work now. Now we want to show that pi is a bijection. So, let's first show that pi is injective. So we are going to suppose that two images, say G1, G2, two images are equal to each other, and we want to conclude that the inputs from the domain were actually equal to each other. So want to show that let me fix my parentheses here. We need an extra one. There you go. We want to show that the ordered pair G1, G2 is equal to G1 prime, G2 prime. And we will do this by showing that the components are equal. So we will show that G1 is equal to G1 prime and G2 is equal to G2 prime. So once we show this, then we've shown that pi is injective. So if the images are the same, just going off of the way that we defined our map up here, this is just going to be equal to, or it's not going to be equal to, this is going to imply that phi of G1 eta of G2 is equal to phi of G1 prime eta of G2 prime. Again, we want to recall that both phi and eta are isomorphisms. The statement here we just wrote, again, these are elements in the codomain, the cross direct product of H1 and H2. So the components must be equal. So this tells us that phi of G1 is equal to phi of G1 prime, and eta of G2 is equal to eta of G2 prime. Since both phi and eta are isomorphisms, so let me go ahead and star this out. So from star, we get to conclude that G1 is equal to G1 prime and G2 is equal to G2 prime. Thus, the ordered pair G1 comma G2 is equal to the ordered pair G1 prime G2 prime as desired. So this is what we wanted. Thus pi is injective. So thus pi is injective. Okay, so the last thing we want to show now is that pi is surjective, and then we are just about done with this proof. Generally speaking, to show that a mapping is surjective, you want to show that for any element in the codomain, in this case, any element in H1 cross H2, that we have an element in the domain such that when you apply the map to that element, it gets sent to an element in the codomain. So let me write that in math terms. So lastly, we want to show that for all H1, H2 in the codomain, that there exists an element, we'll call it G1, G2, in the domain G1 cross G2, such that if you apply pi to this element in the domain, you end up with the element in the codomain. Okay, again, we're going to go back to the fact that phi and eta are isomorphisms. So since little h1 is in h1 and g1 is isomorphic to h1, then there exists little g1. These are just arbitrary elements, but it's the argument that we're trying to get across here. There exists some little g1 in g1 such that phi of g1 equals h1. Similarly, since little h2 is in h2 and g2 is isomorphic to h2, then there exists some little g2 in the group g2 such that when you apply eta to g2, you end up with h2. Okay, since we have the existence of these G1s and G2s, then we can just take G1 and G2 in this direct product, and we can see that when we apply pi to this, just by definition of the way that just from the way that we defined our map, this is equal to phi of G1, eta of G2. This is going to be equal to that ordered pair H1, H2 that we will be looking for in the codomain. Thus, pi is surjective and hence it's an isomorphism. Then we can conclude that hence G1 cross G2 is isomorphic to H1 cross H2. And that will conclude this proof here. Bit of a longer one, but it's a good exercise, I guess.